Math 2414, Trigonometric Substitutions, video 6, another example using tangent. In this one, we're going to integrate 1 over x squared times the square root of x squared plus 4. Recall that the motivation behind a trig substitution is when you have an addition or subtraction problem, usually under a square root, that kind of resembles half of a Pythagorean identity. And if we capitalize on that Pythagorean identity, we can collapse the addition or subtraction problem down to a single term. In this case, the addition problem that we're trying to collapse is x squared plus 4. We're still going to use the identity involving tangent squared theta plus 1. But in order to make our given addition problem match that one as close as possible, we need that 1 to become a 4. So if we multiply this expression by 4, we get 4 tangent squared theta plus 4. And now that the plus 4's match, we can equate the different pieces. We need x squared to be 4 tangent squared theta. And if we square root both sides, we need x to be 2 tangent theta. So that's going to be our substitution. If we let x equal 2 tangent theta, then we need to do 2 things with that substitution: differentiate it and draw its triangle. The differentiation is easy. The derivative of tangent is secant squared. And for the triangle, we will want to isolate the trig function. Tangent of theta is x over 2. Set up a triangle, one of whose angles is theta. Recall that tangent is opposite over adjacent, so we need an opposite side of x and adjacent side of 2. And if we perform the Pythagorean theorem, the hypotenuse will end up being the square root of x squared plus 4. Not a big surprise, because that's the square root that's in our integral. Now that we've identified the substitution, differentiated it, and drawn its triangle, let's make all the substitutions. All right, this one's going to get kind of chunky. All right, underneath the 1, we start with an x squared, but x was 2 tangent theta. So x squared is 4 tangent squared theta. And then under the square root, we have an x squared again, so it will again become a 4 tangent squared theta. But it has a plus 4 after it. And dx is equal to 2 secant squared theta. Theta. Shame on me, I left the d theta off right there. All right, oh, one quick comment, and I probably should have mentioned this a long time ago. If you have an addition or subtraction problem under a square root, you cannot distribute the square root across it. In other words, if you have an addition or subtraction problem under a square root, you cannot just square root each half of that addition or subtraction problem. It's wrong, it's bad algebra, don't do it. All right, let's see what happens here. Based on our choice of substitution, the expression under the square root, if we factored out a 4, would become 4 times tangent squared theta plus 1. That is just 4 secant squared theta. Remember, our substitution was based on the premise of making this very thing happen. And so if we were to put a square root over all that, because it is under a square root, then the square root would just simplify to 2 secant theta. The square root of 4 is 2, the square root of secant squared is secant. So let's streamline all that and see what happens. We have the 4 tangent squared theta. The square root will eventually collapse down to, and I guess I owe it to it right here to finish it off. Theta. But the square root will collapse down to 2 secant theta. And we still have the 2 secant squared theta, d theta, from the dx. And now we start simplifying this. Because we have a fraction, any factor on the top can cancel a factor on the bottom. So the 2's can cancel. And one of the secants can cancel with the secant in the denominator, but we still have a secant left over there next to the d theta. Let's put all this together into one fraction now. On the bottom, we still have 4 tangent squared theta. And on the top, the only thing left is secant theta. All right, we're not out of the woods yet, far from it. But remember, the purpose of a trig substitution is not to do the integral. In fact, the purpose of the substitution at all is not to do the integral, but to change it into different integral in hopes that when you get to that different integral, you figure out what to do with it. All right, so what can we do with this? Well, this is a combination of secants and tangents, and although we have a strategy for dealing with them, the fact that they're in a fraction makes me a little bit uncomfortable. One default strategy for trig integrals is to change everything to sines and cosines. So let's try that on the next page. I wasn't kidding when I said you need to know your Pythagorean quotient reciprocal identities. We've already used a Pythagorean identity, and I'm about to use the other two. Secant of theta is 1 over cosine theta. Tangent is sine over cosine, so tangent squared is sine squared over cosine squared. All this with a d theta after it. Now we have a fraction on top of a fraction, and there's two ways out of it. Number one is to multiply the top times the reciprocal of the bottom. Number two is to multiply both sides of the large fraction by the least common denominator. So in this case, it would be cosine squared. I'm going to multiply both sides of the giant fraction by cosine squared. That is enough ammunition to cancel all the little fractions. In the bottom, the cosine squareds cancel, leaving just sine squared. But on the top of the big fraction, only one of the cosines cancel, leaving a cosine behind. Okay, so now that we got it to an integral of sines and cosines, we can think about our approach for integrating that. We are going to do a substitution, another substitution, because when you're integrating a product of sines and cosines, if one of them is odd, you use the other trig function as your substitution. Since cosine has an odd power, we're going to let u equal sine theta. So another substitution. Let's switch over to green. So at this point, we're going to let u equal sine theta, du equal to cosine theta d theta, and notice that we have the du package ready to go. There's the cosine, there's the d theta. So that means that our integral will equal, the sine squared becomes a u squared, cosine theta merges with the d theta to make a du, leaving a 1 on top. This is an easy integral. Rewrite it as u to the negative 2 power du. Add 1 to the power to get negative 1. Multiply by its reciprocal. And now we have negative 1 over u plus c. Negative because 1 divided by negative 1 is negative 1. And 1 over u because that's what u to the negative 1 means. Now, we're not out of the woods yet. We've done two substitutions, and to be honest with you, I've seen integrals where I've done 3 substitutions before. They are rare. Double substitutions usually only happen in situations like this, where you transform into a trig integral and then do another substitution on it. But if we undo the u substitution, u is equal to sine of theta. So we have negative 1 over sine theta plus c, but that's just cosecant, so let's go ahead and call it that. But we're still not out of the woods because our original integral was an integral of x. So we have to go back to our trig substitution and undo it. And this is where the triangle comes into play. I'm going to go back and forth between the 2 pages. We're trying to figure out cosecant. Cosecant is a reciprocal of sine. Sine is opposite over hypotenuse. So cosecant hypotenuse over opposite. Let's go back to the triangle and figure out hypotenuse over opposite. The hypotenuse is the square root of x squared plus 4. The opposite side is x, hypotenuse, opposite. And so the ratio of those is the square root of x squared plus 4 over x. Square root x squared plus 4 over x. There was a negative in front, right there. Don't forget the plus c. Was it a hard problem? Well, yeah. But I wasn't kidding when I said I truly believe that we are in the midst of the most difficult part of this course. Trig substitutions, which leads to trig integrals, which require a whole different mindset. But this is actually a problem-solving strategy being played out in front of your eyes. You fix one problem, which may create another problem. You fix that problem, which may create a third problem, but at some point, you get to a problem that you can answer. In this case, we got to the problem that we could answer right here. That's a Cal 1 integral. We did it. We just had to do substitutions.